800,000 issues, as I mentioned previously, over a large amount of projects. To say it actually encompasses every open issue between the first semester of 2021. So it's quite extensive. The issues have been extracted using Google BigQuery on an existing data set. And the information that we extracted is the label, so the type of the issue, title description, URL, which could be used as an identifier, timestamps, and the, say, author association. In the data set, we see that roughly 50% of the tickets are bug reports. We have a 41% enhancements, feature requests, etc. And roughly 9% are questions. In the tool competition, we did provide as a template a Jupyter notebook hosted on the Google Colab platform. We hope with this we could provide to many researchers, let's say, equally strong hardware. Obviously, in the modern classification involves some deep learning models which require quite strong hardware, and this is actually a tool that provides for free such strong hardware. Yes. That being said, Oscar will continue with the second part. Thank you.
All right, do you see my screen, guys? Cool. All right, so thank you, Rafael, for the introduction. So we define a set of rules for the competition so that we can have a fair competition. But you know, these are straightforward rules, as in we'll allow fine-tuning, training on the training set, and different manipulations of the data, like feature engineering, data balancing, validation, and so on. And we would use a test set to compute the accuracy, the performance of the models, and we will basically use this data set, these results for the ranking of the competition and declaring the winner as well. What metric we use? Well, we use standard classification metrics, precision recall F1 score, and we asked the participants to provide these details for each label, each of the 3 labels of the data set. And we used the micro average F1 score to have an overall performance of the models. So we would use this metric actually to get the ranking and the winner of the competition. And well, now it's time to know the competitors. So we have 5 teams from different parts of the world. Team 1 is Mohammed and Joanna from the US, from the University of Notre Dame here in the US. We have a team 2 from India, Indian Institute of Technology, Sikar and Tushar. Alexander and Stefan from Clausel University of Technology in Germany. Team 4 comes from Italy, University of Bari, Giuseppe Filippo and Nicole. And finally, our team 5, which is one person, it's composed of one person only, Malihi, from the Netherlands, Delft University of Technology. So I want to take a moment here to thank all the teams that came to the competition. And yeah, looking forward to your talks. Just to give you an overview of the tools that were submitted. So we had a very good variety of models. However, all the teams actually use some sort of flavor of BERT, which is a well-known transformer in the NLP community, and it's been applied quite a bit to software engineering. We had a couple of other models there, XLNet, another transformer, and some baselines. And different information from the issues were used, textual data, also metadata, and different combinations, right? The models had different architectures which combine this information differently or encoded this information differently. And also the teams had standard preprocessing, let's say, techniques here, tasks, with a couple of interesting preprocessing tasks here. So looking forward to know more details about the tools, of course. And well, now this shows the classification results that we obtained for all the teams. The first bar are the 5 teams, and the last bar is the baseline model that we provided. So as you can see here, the 5 bars are kind of really close, right? So we had a really tight competition, which is very interesting. But you can see also that they did pretty good with respect to the baseline, which is, you know, something that we really wanted to have here, right? So as you can see, the last 3 teams actually did almost the same. They were like, you know, very, very tight. The first 2 actually did a little bit better on that. So this slide doesn't reveal any, I mean, who are the winners or anything like that yet. We'll get to that in a second. And if we go deeper into the results of the best model, so these are the results of precision recall and F1 for the 3 labels. And we can see here that for bugs and enhancements, we had really, I mean, the teams did a really good job, the models. But for questions, not so much, right? So something that we would like to see in the talks is to have some insights about why this happened, right? I know the data was imbalanced and so on, but maybe we can get some insights from the teams to know why we had this phenomenon. And this also was found for the other tools as well, not just for the best model that we got. All right, so let's get into the ranking. So as I mentioned, so 3 teams really did almost the same. So they got the 3rd position in the competition. So these teams are, drum roll, Team 1, Team 3, and Team 4. So let's get a round of applause for them. Good job. As for the 2nd and 3rd place, so we had Team 1 or 5, I think. I don't remember the number of the team, so let's get to that. Team 2 got the 2nd place, and Team 1 Team 5 got the 1st place. So yeah, congratulations, well done. And yes, so with this in mind, we switched to the 2 presentations. So let me remind everyone that there is 8 minutes of presentations plus 2 minutes of questions. Please try to be on time because you want to get feedback and questions from the audience as well. And just as a quick reminder, because all the tools did similar things, so we want to have the discussion a little bit more interesting. So you may want to focus your presentations on these aspects that you see in the slides: motivation for the models, details about the models, challenges that you had, features and preprocessing things that you did and how they affected performance, examples of cases of some issues, and maybe ideas on how to move this forward, right? How to move the tool to the next level. That's right. So with that in mind, I'll give the floor to our first presenter, I think is Giuseppe.
Good evening, everyone.
So please feel free to share your screen, and yeah, good.
Let me know if everything is working correctly, if you can hear me, see me, and see my screen.
Yeah, you're totally fine.
Okay, so I am Giuseppe Colavito. I'm from University of Bari, and he represents our participation for the tool competition together with Professor Filippo Lanobile and Nicole Novielli. Our research question is to understand to what extent the text information only can be used for automatic issue labeling. So we developed 2 approaches. The first one which is based only on text, which is the fine-tuning of BERT models, while the second one is based on text and issue author association, for which we use a multi-layer perceptron. To select the best BERT model to use, we split our training set in a smaller training set and a validation set to be fair and select the best BERT model in order to then test it on the test set for the competition. From our result, we noticed that Albert is the worst model, while BERT large, BERT base, and Roberta are the best. We selected Roberta because it had a better F1 on the question class, since it was the hardest class to recognize. while the micro F1 is very similar. The preprocessing we used is based on regular expression to recognize image, link, codes, and another tool which is ekphrasis, which recognize other components of the issues, and to substitute them with the custom tags. Then we concatenate title and body and do the standard BERT preprocessing, which is encoding text and then do padding truncation to reach 128 tokens. Here are our two classifiers. The first one is based on fine-tuning of Roberta. We obtain the prediction of the issue label. Then we extract the embedding from the Roberta model, which is already fine-tuned. And then we concatenate the one-hot encoding vector of the issue author association to give it to feed it to a multi-layer perceptron and obtain another prediction which embeds some kind of non-textual information. From the result, we can see that Roberta is the best model. MLP cannot achieve better performance than Roberta, but we can see that recall is better for the question class, which can be explained by the fact that, for example, questions are mostly asked by persons which are nothing for the repository. They are not collaborators, not members. They are just random user going on the GitHub page and writing an issue. We perform them some error analysis in which we can see that it is easy to understand that the question class is very underrepresented. So we have that the main causes of errors are question misclassified as bugs, enhancement misclassified as bugs, and questions misclassified as enhancement. So then we manually analyze 300 and more than 370 comments, which are a statistically significant sample of misclassified cases. And we find out that for the case of question misclassified as bugs, there can be some questions which are reporting inconsistent behavior, missing code, or maybe they contain error messages, which is the standard structure for a bug report. So if a bug report and a question contain exactly the same elements, how can we disambiguate between these two kind of issues? I report here an example in which there is a description of an error and how to reproduce it. This question, this issue is labeled as question just because the member of the repository knows the expected behavior of the code and then says, okay, this is the expected behavior, this is a question. But if that wasn't the expected behavior, it would be probably labeled as a bug. So how are we going to handle this fact that we don't know which is the expected behavior from text? If we analyze only text, we cannot understand which is the expected behavior. Then a question or bugs can be misclassified as enhancement when in an issue there are suggestions for fixing the problem. So they can be misclassified as enhancement. And there can be also inconsistencies in the labeling rationale. Since the issues come from different projects, different community members can have different interpretation for the semantics of the different labels. For example, in this case, we have a question, which is labeled as a question from a contributor. And then since the feature for which the question is about is not available for the project, the collaborator labels it as an enhancement. So this is basically a question, but for the collaborator, it is useful to flag it as an enhancement because he wants to add that feature. And in the dataset, this is an enhancement. This is labeled as an enhancement. Then there are also some issues which are not in English. So a language model which is based on English will not be able to understand anything. As a future work, we plan to explore a more effective way to embed non-textual knowledge. Then also try project-specific training to wrap better the labeling rationale, which can be different for the single projects. and then do some quality assessment for training data, since there are such as small projects which maybe cannot be trusted for the labels that are available, and then can introduce some noise. So I ended here my talk. If you have a question, feel free to ask. Thank you.
Thank you, Giuseppe. Big round of applause to Giuseppe for the nice talk. And we open the room for questions, and there is one that was asked on the chat. I'm going to read it out loud. The question says here, while training the language models, I saw that all of them were trained on a different number of epochs. Roberta 4 epochs and Bert base 2 epochs. I would wonder, why was this done? As Albert.
Yes, we wanted to understand which is the best number of epochs which can achieve the better performances. Since the models are different, we cannot assume that every model needs the same number of epochs to get to be trained correctly, let's say. So since we use the validation set, we are not unfair if we try different epochs or hyperparameters.
Right. I didn't finish the question because there's an explanation about the question at the end. So it says,
okay,
Albert is a light model, so it should intuitively be trained a bit longer to capture more information. So what do you think about this? So the question is, can the authors explain this choice of epoch selection a bit further? Yeah.
Yes, just we saw the performance for, we selected to train all the model for five epochs. And then we saw all the performance on the validation set. We saw that, for example, for Albert, I don't remember well what was the number. We selected three epochs because in a range from 1 to 5 epochs, the third epochs gave us the best performance. So we kept that model and compared with the other best model with the best number of epochs. I don't know if I was clear.
And Barish, do you want to clarify maybe, or? Okay, good. Is there any other question? There is another question. Go ahead, please, Ali.
Yeah, hi. Thank you for the talk. I was wondering, for the problem to hack the problem of misclassification of question to other two categories, do you think, Giuseppe, that a sentiment analysis component could be helpful? Like when a text or issue report is labeled as confused, could be helpful to categorize it as a question?
I think that, yes, we can. One of the things I would like to try is to add some other feature we can be significant to help the language model. So as we add the issue-author association, it would be nice to add also sentiment analysis components, but also other kinds of feature that can be, let's say, a proxy for understanding when an issue can be, it's more likely to be a bug or a question. So yes, it can be useful, I think. Thanks for the question, of course.
Thank you.
All right. I think, is there any other question? I think we have a couple of seconds for one more question. All right. Thank you, Giuseppe.
Thank you.
Let's move to the next presentation. And is the next presenter available, Mohammed?
Hello, everyone. Can you see my screen?
Yes, I think so.
Oh, thank you.
There you go. Yeah.
Thank you. I'm Mohammad Latif Siddiq, and my professor Joanna Santos from Security and Software Engineering Research Lab from University of Notre Dame. We are going to present our work, BART-based GitHub issue report classifications. The organizer already discussed about the problem. We are just jumping to the approach. First, the organizer already gave us the data set. We process by taking issue title and issue body and doing some preprocessing by removing blank space. Then we encode the data and tokenize the people's data feed into a part-based model. We set the model to evaluation on the test data set. The organizer gave us the training set and testing set. The training set actually contained 90% of total data, and testing set actually contained the 10% of total data. But we later split the original training set into a new training and validation sets. The new training set actually now contain 76.4% of total data, and the validation set contains 13.5% of total data. We are using BART-based model. There's some motivation behind that. One is it was the state of the art of NLP tasks when it was released. It doesn't require any substantial architecture modifications. It was a new standard of P10 language model. Later, their release of new language learning model like Robot T5 and GPT-like model. And another thing is there's available open source course and tutorials for learning this type of models.
Mohammed, are you with us?
I think it's frozen.
It's frozen. Okay, we lost him. Let's see if he joins. Yeah.
Sorry,
Mohammed, welcome back.
No
It's all
problem.
right. It's all right.
Thank you. Sorry, can I see my screen again?
Yeah,
It's loading. Yeah, we can see it. Yeah.
Yeah,
Sorry about that. So we are going for feature engineering processing. First, there is several metadata in the data set. We just take the issue title and issue body combined into a new metadata. We are calling it issue data. Then we use Gensim library to remove blank space and convert it to feature. Then we do the encoding. We use BART tokenizer, and for tokenizing, we use BART base uncase. It will not differentiate any capital small letter case letter. And with several parameters for that, like it add special token, we are encoding special tokens, and we want to get attention marks, and we paid the longest sequence in the data batch, and then we truncate the acceptable input size of the model, and we want to tensor in PyTorch tensor. And there's hyperparameters like we are using. Sorry about that. Sorry about that. Can you see my screen again?
Yes.
Sorry about that. I think it's a network issue here. For hyperparameter, we use BART-based uncased P10 model. For optimizer, we use AdamW with running rate 10⁻⁵ and epsilon 10⁻⁸. For running rate schedule, we use linear schedule with warm-up. For the model result, I'm just here presenting the F1 score. The baseline model is FastText, and we are having in the FastText, the global F1 score is 0.8162. Our base approach gets in EPUC 2, it was 8586 as an F1 score. There is some examples of predicted cases, like for simple, we just provided the title here. For example, a database backup to Dropbox none, actually correctly classified enhancement, cannot add HP to wall none, is actually bug, and how to prevent dead loop is actually question, and our model correctly classified it. And there is sample which didn't get the correct prediction, like model not found error, no module name hello. It should be a bug, but our model predicted enhancement. Another thing is software development reaction with the title. It should be a question, but our model actually predicted it as a bug. There's some improvement idea, like we are using current part, but we can explore new state-of-the-art P10 models like GPT or T5. We can pre-process data by removing duplicates, use elements like image and course. We can creating balanced data set because currently there is only 9% of the questions. So we can create a balanced data set to explore how it performs in a balanced data set. We can explore different hyperparameters. There is some challenge in training and evaluation. For example, we have to share we have to use GPUs in our cluster. So there is sometimes hard to get GPUs. There is a problem. Another thing is sometimes it's unfit for larger base size. But the authors of the byte actually suggest to use 16 or 32 as a base size, but we have to use 4 as a base size because the shared GPUs are unfit for the larger base size. Another thing is the training actually time consuming. Fast takes actually very fast to give you the result, but for P10 model, it will take longer. Like for training, we have to wait 18 hours per epoch, and for testing, it actually takes 6 hours for running the full 4 epochs on a train set. Thank you. Is there any question?
All right, thank you, Mohammed, for the presentation. Is there any question from the audience for Mohammed? Questions? Okay, maybe I can ask a question.
Sure.
So, and actually, I observed this case in the previous presentation, but I don't know if you observed it. So essentially, some misclassification may be due because there are some keywords, right, that are found maybe in some bug reports, some issues sometimes, right? But they refer to, they use the keywords, but because there are keywords and so on. I mean, these keywords can be used in different types of issues. That's what I'm trying to say. And actually, I saw that one of these keywords is kind of the template that GitHub projects use, like observed behavior, steps to reproduce, expected behavior. So I don't know if you observed these cases, like, these templates have like a negative impact on the performance for some of the types. And I don't know if you have some ideas on maybe what if we remove these labels, right? How can the models perform?
Certainly, we can do that, I think. Sorry, I cannot understand your question. Can you repeat it?
GitHub projects use a template for issue, right? And sometimes there are titles in the body, right? For example, steps to reproduce, expected behavior, observed behavior, right? And these are templates that are found for different types of issues as well, not only for bugs. So, and also because people make mistakes, right? Sometimes you use, write their thing and they don't worry about the type. So I'm wondering if you found these cases where maybe these titles had a negative impact on the performance of the models, or, if we remove these titles, would the models do better?
We can certainly explore that. I think we didn't explore this type of things, but we can certainly explore in our future work.
All right. Any other question? All right. I mean, I think we can move to the next presenter.
Thank you.
Thank you, Mohammed. The next presenter is Alexander, I believe.
Yeah, hello.
Hi, Alexander.
Oh. Nice. Can you see my screen?
Yes, we can.
Okay. Yeah, well then, hello. As said, I'm Alex, and I'm presenting a work I did together with Steffen Herbold, predicting issue types with ZBERT. Okay, ZBERT, or Software Engineering BERT, is basically a BERT large model which we pre-trained exclusively on software engineering data for previous publication and which we used in the Drew competition. And yeah, as everybody basically used BERT, I'm going to not talk about a lot of BERT stuff, but the stuff surrounding the actual tool. To give you an overview, we're using our pre-trained model, seebert, combined it with the HPC resources provided by our university and the training data provided by the tool competition to create a fine-tuned model of the pre-trained model, which we then later wrap into a worker process, which in turn is connected to a message broker so that we can do live queries and stuff from the website accompanying the publication. A bit more information about the pre-trained model. It is, like I said, basically a BERT large. It only uses lowercase tokenization and a maximum sequence length of 128 tokens. The pre-training data sources are GitHub, a large chunk of GitHub data, so commit messages, issues, a Jira dump, and Stack Overflow questions and answers and comments. So why did we do this? We noticed that software engineering language is sometimes a bit different. Here are 3 examples from the data where we have basically the masked language modeling task. So this is basically how you pre-train a model. You have a mask and the model predicts what is the most likely word that fits there. And BERT usually gives more generic answers. So for the first one, fixed RTOS masked warnings, BERT says AND, which would make sense in a more generic context, and seebert says compiler, which would make more sense in a software engineering context. The same for the next, especially as we're talking about issue type classification, mask on opening profile page, BERT says click, which would again make sense in a general context, and seebert says error, which would make more sense in this case because this is basically the entirety of the bug report. And the next one, scorns mask when a node depends on a binary, BERT says occur because the information about the other stuff in the sentence is missing, seebert says fails. Regarding pre-processing, to be honest, we did not really do a lot of stuff. So basically, we just took in all the data without filtering, concatenated title and body, and then stuck it into the model. Yeah, this is basically how we got the results. If you have done this, basically not pre-processing the data correctly, not pre-processing the data at all and stuck it into a BERT large, I would be interested about in the results. Yeah, the fine-tuning process is basically very simple. We split the available training data 80-20 and basically run a best of 5 epochs. So we are training the model for 5 epochs on the 80% of the training data, and whatever epoch is best on the 20% of the holdout data is then used as the final fine-tuned model. The implementation is also very simple, basically run-of-the-mill PyTorch dataset for the text. And we are wrapping basically, or we're creating a scikit-learn classifier which wraps high-level Hugging Face trainer interface. So that can be used in a scikit-learn pipeline. We didn't end up using it because we did not do any hyperparameter tuning, but I thought that was a nice detail. Coming to the results, we were able to improve on the baseline in every case, most in the question part. Maybe that's where the larger language models are really shining or better improving upon the smaller language models. So to the website part, this is basically an example. So you can type in your own sentence, try it out, or use some of the examples from the data that we have selected and look at what the model does give you. This works really nicely, and the inference time is not that long. You don't really need GPU resources for only the inference. So we could basically stick it into a worker process, provide a lot of memory, and if you load the model into memory in its completeness, you can have nice results in a timely manner. So some examples what did work and what didn't work. At the top, we have examples for what our model predicted correctly. At the bottom, what it doesn't correctly. Red indicates a high reliability on the word. So if a word is red, the model has a bit more attention on this word, and blue is the opposite. So for the first example, does this library support for tagged union? Does this library is indicative of the question label, and our model correctly labels this as a question. Support is more indicative for an enhancement, but it was not strong enough to get labeled as an enhancement, basically. The check mark on the right indicates what is the correct label. For bug, we can see that doesn't is a strong indicator of a bug. For enhancement would be just profile settings, home, but this doesn't really come into play here because doesn't is such a strong indicator. What didn't work, we can see create new fav icons. Our model classified this as an enhancement because of create and fav icons, but the data says this is a bug. So our model was wrong here. The last example, when player attempts the same level many times, this point should reset, is bug. Our model labeled this as an enhancement, but barely. So it was near the bug labeling, but the enhancement won in the end because attempts is a negative influence on the enhancement, and basically many times should, and should is the strongest indication. So these scores are from a tool called SHAP. If you want to try this out, they have a very nice library for transformer explainability. Yeah, and that is already the talk. So we basically took a pre-trained model that we have pre-trained on software engineering only data, did almost no pre-processing or hyperparameter tuning, stuck it into the model, performed a fine-tuning on this multi-label issue type classification, and we are able to get some performance improvements across the baseline. And below are links to the website replication kit and the Seebert preprint paper. So basically the paper for which we built Seebert. That's it from my side. Thank you for your attention.
Thank you, Alexander. All right, we open the floor for questions. I see Rafael has his hand raised.
All right.
Go ahead.
I get started. So I have a question regarding, so you mentioned before that you did not apply any specific kind of pre-processing.
Yes.
So I'm interested in, now in retrospect, do you regret that decision?
I mean, we could probably have a better score overall if we did perform pre-processing. Yeah, so I kind of regret it, but I'm also happy to hear about others who maybe have done some basic BERT stuff without any pre-processing or with its limited level of pre-processing, to see how this compares to a model that is exclusively pre-trained on software engineering data versus a model that is trained on basically Wikipedia and Wikibooks.
Yeah, thank you.
Yeah, okay, so Stiano, go ahead.
If I can join. No, let's say, of course, I liked all the presentations so far, but this one, make me wonder. No, there is the baseline of the competition is fast text, and sort of it's very sensitive to preprocessing. We have seen with Rafael and Andrea in other works where if you make a preprocessing, will not really work well. It's not always the case, because really fast text is very sensitive to semantics. You were shown this nice example of don't or should and shouldn't, and that's very important. And when you go to BERT, what is your feeling about that? You need really proper processing? You expect the processing will improve really, or is not really that the case? Because no, we had very, let's say, unexpected finding when tried to do, okay, we will do pre-processing, we grow 10%. We actually did not get any. So do you have any expectation on that?
Yeah, I think pre-processing, would improve it. So when looking at the data, so what is usually misclassified is something like a different language. So if it is like Korean or Italian or something like that, it is not classified correctly because we are only trained on English, obviously. So maybe filtering that out from the training data before fine-tuning would increase the performance.
Okay. Thank you.
All right. We have one more question from Dominic. Please go ahead.
Yes, it's not actually a question about this specific paper, but I just had a quick thought about this overall approach. If I understand it correctly, at least the approaches so far mostly try to use the existing keywords to as the basis for the classification. So I think you just mentioned that, or you said that the token doesn't, for instance, gives a strong indication that the question might, or the paragraph might be a bug, for instance. But I was just thinking whether it might make sense to explicitly model the absence of some information for a different classification. For instance, if we have, I took a screenshot of one of your examples here, so I just want to read out the one of them. You said, but profile settings, yeah, right there in the middle one. Profile settings, home back button doesn't work, and then it classifies it as bug, correctly?
Yes.
Yes, but it might maybe also be enhancement. Maybe it might be a good idea to explicitly model that some information are not included in this example and therefore give a more accurate prediction. Like, I don't know, maybe there's some certain keywords that, or not necessarily keywords, just, yeah, in general, absence of information. Maybe that's a point to discuss that just crossed my mind really.
Yeah, we should keep in mind that this is a large language model that also takes context into consideration. So it is not just basically a keyword mapping or even a word embedding. But it takes the whole sentence into consideration. So if the sentence would be different, would have a different color.
So you mean that the absence of information is kind of indirectly within the model already?
Yeah, I would say it is in the model indirectly. So
yes,
I mean, this is kind of a simplistic, if you will, scoring function of certain words. Yeah. But we should keep in mind that this will change depending on the rest of the sentence. So because these large language models with the attention mechanism, take basically the whole sentence into account. And so it is, if the sentence would be different, like I said, would have a different color. So it is not that simple to say, okay, we can just remove keywords or plan for different keywords or something like that.
Yeah. Okay.
All right. Well, thank you, Alexander, for the nice talk. And we're going to go with the next one from Shikar or Tushar. Tushar, I think, yeah.
Hi everyone, can you hear me and see my screen?
Yeah. Yes, we can.
Yeah, hello. So my name is Tushar Karan. I'm currently a master's student in Indian Institute of Science. So let's start. So the methodology that we applied to solve this problem is like, first we formulated it as a standard multi-classification problem and used cross entropy as a loss to train all our models. And in the pre-processing step, like before applying anything, we perform exploratory data analysis to provide it on our provided data set to design distinguishing features for the classification parts. And what are those features? It's like the first feature is about early issue. We observed that like the issue number, that is one of the metadata in our data set, like earlier issues were mostly contributed by the enhancement request. So maybe we thought maybe issue number might help us to determine whether it was an enhancement bug or what is the type of the issue, using only the issue number. Second feature that we suspected that might be helpful is it the owner opened issue? Like mostly the issues opened by the owners were enhancement issue, and these are all the observations that we get from like while doing the EDA on the data set. And the third feature is about the question title. So questions in the issues like follow certain sentence structure. Like more like we know that like most of the questions will start from WH word, or let's say the particular question, like questions have particular format in grammar. So, and as we know from other participants, like the model was performing very poorly on this class only, the question. So that's why we thought of using this, like, is this a question, a feature, a binary feature for using in our model? So let me move on. So this was our model architecture, and we concatenated the issue title and the body text and gave it input to the BERT model. And the CLS token, which is a classification token, the embedding for that CLS token. And again, after concatenating with these three manually created features from the dataset, the early issue, is the issue opened by the owner, and is it a question? So these are the three features, and we again applied binary variable embedding layers on these three features because these are like numeric and binary features. And after concatenating the whole, these four things, we finally applied a linear layer and the softmax layer to classify the type of the issue. So what are the steps that we followed? So first of all, to create a validation data set, we sampled 1,000 samples from the training data. And sampling is stratified so that like we wanted to maintain the distribution of classes. Like as we know, the question, there is a quite of imbalance of data imbalance in our data set. And that's why we did the stratified sampling. And in the pre-processing steps, we use regex-based substitution. So like there were a lot of code snippets, URLs, usernames in the issue text. So we removed those and substituted with some text, let's say code, a special symbol for code snippets and inline codes. We removed all those new line characters with the spaces. And finally, what was the motivation for these pre-trained models? So we observed that like the body length of issues were not greater than 512 words, and the title was even, most of the titles were less than 50 words. Hence, we employed the BERT-style model to capture this long-term context from the issue body and title without worrying about the text length constraints for such models. And why BERT? Because we know that BERT is pre-trained on large corpus of English data, and we can make use of the transfer learning. The another model that we tried from the BERT family was CodeBERT. And the motivation for using this CodeBERT model, as it was bimodal pre-trained model, and the programming language and natural language corpus. And the idea was like we might be able to leverage these model trained on both the things, programming language and natural language, because in our data set, there were a lot of code snippets and inline codes. And finally, the last model was about Roberta. And as we know, it's like the corpus for pre-training Roberta is much larger than the BERT. And that's why we suspected that this might help us to get better accuracy. So to analyze like why for certain classes, the model was giving better accuracy, and for certain classes, it was not giving better accuracy. We extracted the embeddings just before the final layer. So like after concatenating the BERT embeddings and the embeddings from the our handcrafted features, we then there's the Tesny plots and PCA plots, and as you can see, like the blue dots are question classes from the question, green dots are from the box, and finally the orange ones are from the enhancement. PCA plot shows that the question, the samples from the question class are like quite spread across both these classes, even in the TSNE plots also. And that's why model was not able to clearly distinguish the questions. And as explained by other participants also, this might be because like there are some wrong labeling in the questions, and sometimes like the question might be from the enhancement as well as from the bug also. And yeah, and these are the results that we got after training. So as you can see, like the code-word model was performing better for certain class, like let's say for the bug, it was giving around 88.88 precision. And for Roberta, without the hack design features, were giving the best accurate, best global F1 score, which is 86.53. And some of the ideas that we think to improve are like there is a lot of data imbalance, and maybe we can use various weighting techniques to weight a particular class, let's say question, to incorporate like the data imbalance in our data set. And Roberta style pre-training on domain specific data. As we know, like word style models are trained on English corpus, but maybe domain specific pre-training might help. And finally, the ensemble of these models might help us to increase the accuracy. And another idea we think is might help is use of contrastive loss. And I have given this. What is contrastive loss is, I guess one of the participants used the sentence transformer for using for solving this problem, but I guess the previous participant doesn't use pre-processing, data pre-processing, and I suspect with the pre-processing and using contrastive loss might help us to increase the accuracy. Yeah, thank you. Any questions?
All right, thank you, Tushar. And we have one question, I think I saw. Yeah, from Ambarish. Go ahead, please.
Yeah. Hi, Tushar. Great work. I just wanted to ask you, you proposed in the end that you would use ensemble to improve the accuracy. I was wondering, how would you implement it? Like, would you implement as an ensemble of shallow models like we do in boosting, or how would you do that?
Yeah.
Like, would you go that through a random forest model, overfitting on several models, or then would you look at the bias variance curve using numerous shallow models or using different BERT models? How would you do that essentially?
Yeah, so basically the idea is, as you said, like the boosting, we suspect like there are some smaller models that we can use for this. And maybe like I observed that in code-word models were giving better performance on some classes, and some models trained on Roberta were giving better performance on some other classes. Maybe these 4-5 models we can use for ensembles. And as you said, maybe boosting, and by observing bias variance curve, we can use that as a for ensembling. Yeah, is like, was I clear with your
Yes.
question, or?
Yes, indeed.
Yeah.
You were quite clear. One more question, but it's it's a bit different. So based on the data that you got, and given that you had some imbalance, or assuming that you had a balanced data set, how would you say that do you weight each class of your classification task equally important because you extend it to using ensembling? So like, would you say that every class has an equal weight, or do certain bugs or the class bug would be weighted more while using these ensembles? Or how would you, like, just a inquisitive question? Not, yeah.
Yeah, for handling data imbalance, we might use, like, if the model is not performing well on particular class, we might increase the weight of that class, so that if model makes a mistake in the particular, like in predicting a particular class, we might give more loss to that particular prediction. So by doing that, like giving a more weight to, let's say, a question class, because model is not performing good on the question class. So if model makes a mistake in predicting question class, we should give more weight to that class.
Indeed.
So these are one of the ideas. Yeah, one of the ideas that we can use.
Okay, thank you.
All right. Thank you to Shah for the nice presentation. We are moving to the final presentation, which is the winner of the competition. Who is the winner of the competition, Malihi? The floor is yours.
Hi, let me share my desktop. Can you see the slides? Okay. Hi, everybody. My name is Maddie. I'm a postdoc researcher and lecturer at the University of Delft in the Netherlands.
One quick comment. We are seeing your presentation screen for you, not the actual full slides, just for you to know.
Okay, let me. I wondered maybe. Are you seeing it fine now?
It's loading. Yes, we see it. Great.
See it? Okay. Okay. First of all, thanks from the organizer for organizing this event, and thank you all for the participants for participating in this competition and the participants joining this presentation. Others talked about the problem, so I will directly go to the model itself. My tool has this overall workflow. There is two main components, the data component and the model training component. The training set that we got for the competition contained over 8,000 issues from 3,000 repositories, and we had 3 labels for categorizing. So this was a multi-class classification problem. For processing the textual information, I first looked at the data, and I found that there are over 26,000 issues that are duplicated in the training set. So in order to train my models faster, I removed those duplicates. Then I normalized the text, and by normalization, I mean replacing some parts of information such as function names or issue numbers that increase the size of vocabulary, but do not convey much information as is. So I replaced them with a placeholder, and then I converted my text to lowercase. Next step was cleaning the textual information. For cleaning, I removed punctuations, non-ASCII characters, and consecutive white spaces. And then I truncated my input information. All of these models have a limited input sequence, can be fed a limited input sequence. So I looked at the statistics of data, and I observed that issue titles on average had around 6 tokens, and issue bodies on average had around 50 tokens. The median number for the latter was 100 tokens. So to be precautious, I set the cutoff point at 200 tokens and truncated all my data at 200 tokens for feeding the models. And at the end, I combined all of my features, which I will talk in the next slide about, and fed these to the model. So the features that I included are the title of an issue, the body, the author association rule, and the repository name. The reason for this is that I observed that more than 8,000 of issues didn't have a body. The titles were short, so I thought that maybe adding more information can help the model understand the issue a bit better. Author association rule could contain several values such as owner, maintainer, contributor, collaborator, member, or mannequin. And others also talked about this, that maybe some type of authors would write different types of issues, so it can convey some sort of information for the model. And yes, I concatenated all of these and fed these to the model. The model itself is a Roberto model. Because the competition focus was on accuracy, I chose this model. Difference between Roberto and BERT is that it changes the pre-training tasks a bit. If I remember correctly, it uses a dynamic masking instead of a static masking. compared in what is used in BERT model. And also it gets rid of the NSP task, the next sentence prediction task. And doing so, it's able to optimize the performance and improve the accuracy of the model a bit. So as I said, because the focus was on accuracy, I chose Roberto, but other models such as Distilbert or Albert can obtain comparable accuracy result, but they are much faster and smaller models. So if the focus would be on other characteristics of the model, we can go with other pre-trained models. And then we add a fully connected classification layer on top and get the predicted labels. So as for the results, I included ticket tagger, the baseline using the competition, and a logistic regression as a traditional classifier. And we can see that for all of them, CATIS is able to outperform the baseline. One important notion here is the question category, which is performing less than the others. My speculation was that it's, first of all, it's less represented in the data, and also it can contain more diverse information with a more diverse vocabulary. For example, bug and enhancement category are more focused category. But we can see that using pre-trained models, questions can benefit a lot, maybe even more than the other two categories. So for future work, I would focus on using balancing techniques for a better accuracy across all categories, because the data was imbalanced. Another improvement can be by using a more fine-grained category set. For example, dividing the bug category to several types of bugs, or dividing the question category to, for example, question category, support category, etc. And my last suggestion would be to use source code analysis, because right now my model is based on a pre-trained language model that is trained on textual information. And when fine-tuning, I'm also focusing on the textual information, but a model that can perform source code analysis and learn source code can also help the performance of such models for issue classification. And finally, thank you for being here. If you need to know more information, the code of CATIS is available on my GitHub. The preprint of the paper is also available, and here are my contact information. I'm happy to take questions.
All right, thank you very much, Ali. And I see Andrea has one question. Please go ahead.
Yeah. Do you have statistics about the duplicated bugs?
The duplications were, I think, 26,000 issues.
Which class is more affected by the?
No, to be honest, I didn't check. Yes.
Okay.
But it would provide a good insight. I'll check it later.
Okay, thank you.
Rafael, go ahead.
Yeah, thank you, Mali, for your presentation. So, question from my side. You did mention your pre-processing pipeline, and it seems like in your case, that's the magic sauce that made everything work so well. So I'm wondering, is there any pre-processing step, any heuristic that you didn't try but you think might work really well for the future?
See, I have other papers on this domain on GitHub issue specifically, and in those studies, removing URLs and paths could definitely reduce the vocabulary size. Other type of them, let me check. No, that's it. I think that on top of my head, that also would help. Yeah.
Great, thank you.
Very cool.
All right. Are there any more questions? All right, I don't see more questions. So let's thank the speaker and congratulations for winning the competition. Very good job. Very interesting work as well.
Thank you.
All right, so thank you all the competitors, all the teams for participating. As a schedule, we have now a few minutes for some discussion. And the idea is to have some sort of chat or discussion or conversation about things that we can do in the future in terms of tool competition, things that we can improve as for the workshop and so on, and well, also additional questions for the presenters as well. I apologize, my camera is off right now. I have some technical difficulties here, so yeah. So I invite the authors to turn on their cameras to have a discussion here, please. If you can turn on your cameras. All right. Cool. Sounds good. All right. So, one initial question that I have for the authors and for everyone actually is, all right, I mean, we saw the performance of the tools, right? And the improvements among them were not substantial. The differences, right, were not substantial, right? Sure, there was some extra preprocessing in some tools, some feature engineering and so on, right? But the question is, how can we make substantial improvement here? I don't know if any of you have ideas on that. Or is there a limitation of the models? We need better models, we need better data, or what do we need, right?
Can I answer?
Sure, go ahead.
Okay, in my opinion, the data is a strong limitation. As I said in my presentation, in my opinion, the data has to be collected in a way that we can, let's say, we can trust the labeling. In this way, everyone in the web can potentially flag an issue as a bug, a question, but it is garbage. Let's say it can be garbage. So I think it is an attempt, but for a stronger study, let's say, we need to have some criteria to label issues. Maybe it has to be done manually. Of course, it is hard to do do it manually and have the same amount of data. But I think that the labeling is not quite good in some cases.
I echo that concern as well. I mean, garbage in, garbage out, right? If we don't have good data, then there is no way the models would be able to learn something useful out of it, right? So yeah, this is a concern as well.
So can I jump on the conversation to warm up, hopefully, the area?
Yeah.
I was doing a study actually with some colleagues. I work on a project for DevOps for cybersecurity system, and there we had to analyze manual issues from cybersecurity system, robotics, drones, self-driving cars, whatever you think may have a physical dimension. And these are not software engineers, they are not developers. They don't even tag correctly the issue. And they even don't tag them at all. So there the problem is really to label that. You don't really have an exhaustive data that may work for them. Have a different terminology, different tokens, different terms. If you try to train from software engineering the repository developed by developers and try to classify it with them, I think it may not work. And also there you have more a safety dimension, which you don't have in most traditional systems. That's hopefully create a bit of a couple of challenges you may be interested to jump in or look into the future. So let you tool competition talk.
Absolutely. Any comments on that or any other thoughts?
If not, I will have a follow-up question. Also again to the participants. So yeah, Giuseppe, fair criticism. I mean, yeah, trusting the labels, it's a big issue, right? But I'm wondering, so besides, let's say, the quality of the source of truth, could we perhaps, is there a way to enhance the data sets in a way that, we provide, is there some metadata that you could get, with the existing issues that would help you classify better? What do you think?
Okay,
Generally.
in this direction, I actually tried something such as using stars or the number of collaborators, count of the issues that are in the data set. But as I saw from the numbers, let's say, having more data usually leads to better performance. Of course, for some filters, I was trying a filter on stars, let's say. The performance are still very similar. So I used, for example, 200,000 issues for training a model that has substantially similar performance with a model that used 800,000 issues. So that's something that has to be understood, let's say. So maybe we can find some filters to check whether some issues are or some repository can be trusted or not. But still, we are not very sure even with this.
Yeah, fully agree. Does any of the other participants, given this criteria, selecting the data points to train your model with, does anybody have a comment on this?
So more generic. I don't know. Maybe I try to help again the conversation. So you now have sort of trained the model. You have focused on the 3 labels. Of course, that has been given by the issue competition chair. But if you wanna take the tool that you have now and you wanna make it work in an industrial setting, imagine you have a company that using GitHub issues to prioritize their workload. What would be the way you will validate there? So here you have open source data that you don't know how to trust it, how you make or you create a data that is like trustworthy, working with a company. What would be the right way to do it? It seems to be a very important topic. Maybe you have an idea.
In my opinion, this is also a way to justify, to motivate the need for automated solution, because here the problem is the ground truth, and in my opinion, a way to have an evaluation, a validation of already labeled data should be a need for software engineering domain. What do you think, guys?
Too shy, I think, a bit. There's no wrong and right, just opinions we are sharing here. So don't feel, worried to reply.
I don't know if I understood correctly the question. So could you please repeat it?
It's not a question, it's just an observation. I think that this discussion motivates the need for automated solution in this context, because the problem here is the ground truth. Can we trust developers? Can we trust who label the issues, no? And in my opinion, this is a question that the software engineering community should address in any way.
Yeah, I tend to agree with Andrea, right? As we develop better tools, right, that will help create better data,
Yeah.
right? But it will take a while, right, to create, to have data in these repositories that are high quality. I mean, I don't know how often actually these tools are used in practice. I've seen a couple of papers, right, where they actually use it, and it's they have shown studies. I think there is one recent one from the MC Journal where they actually looked into how these tools are implemented to deal with issues. And I think it's been quite successful, right? And it's not only about accuracy, it's only about changing the processes in a company on how to manage issues.
Yeah.
And they showed that actually, yeah, I mean, the tool encouraged the team to better manage bug reports and issues, and to better create better processes to handle issues. And I think that's very important as well.
I think there is a question from the audience.
Yeah, I was just going to have a comment on that, and I agree. And I think if I just thought if we could have a model to cross-check these labels, would be beneficial as well. So I thought maybe we could check the way that these issues have been addressed. So if it's a bug, I expect it has changed some part of the code. If it's an improvement, it have inserted some code that wasn't there before. And if it's a question, it's just have been answered by text, not a code change, right? What do you think?
Yes, of course. In this case, you need the issue to be linked to a code change. So again, you need to retrieve the metadata. That is a thing that you can do, but maybe in some case the issue is not linked. Of course, you have to understand what are the practice of the developers of that the repository. So you are again relying on the developers. So you have to find the right projects to do so.
Yeah,
that's right. That's right. Maybe use only the subset of issues that have this link.
Yeah. Perhaps, I mean, this is a valid approach, I think, for a company that already enforces such practices, right? So if by convention in your company you have to associate a commit with a specific issue, then this data exists. So for that company, we could create, we could use this approach. Right? Yeah.
So since we are approaching more toward the end, sort of a few more minutes, maybe you participants of the competition or anyone, do you have feedback for next year you could integrate? We're talking about the true trustworthiness of the label. You talked about, for sure, we will try to integrate mainly Rafael, Oscar, and probably also us eventually if needed. How to improve the data set for next year or the competition. We are happy to have feedback via email, but it's also, I think, it's the right moment to have some input to us. We could integrate and annotate, and then for next year we'll improve your experience. Do you have any anything that you want to have for next year?
Unless you want to annotate 800,000 issues. I don't know.
Crowdsourcing or next year for sure.
If you guys have ideas on, what kind of task we can have for the next edition of the competition, it doesn't have to be issue classification, right? It could be other ideas, other tasks.
Yeah, next year we already have some ideas we'll tell in the end, on the closing, having different other tasks. Not only, we will keep this one, we'll have new ones. So we'll be able to improve your own tools, but you will be able maybe to try it out in other problem. That will be our promise. We will do it. Of course, we are happy to have input from you.
Competition with multiple tracks or something.
Yes. But essentially, you could really have the same model using in different contexts, and maybe in some tasks will not work as you expect, while in others will actually work well. So that will one of the things we could try to foster for next year. Of course, you know, maybe I work on this specific problem classification, which is not really GitHub issue, and then maybe you want to have this next year. We try to make it happen. You know, that could be an option.
So I have 2 ideas, let's say, for next year, how we can improve the competition. I just like to hear from the participants what they think. So one idea I want to incorporate is, and I'm actually surprised nobody mentioned this. So we just had these 3 like issue types, and they were like, when we did the query, we matched for exactly the keyword, but obviously there's many synonyms with this kind of keywords. So first I want to know, are you interested in having a expanded data set where we include, say, common synonyms for these labels? That's one thing. Yeah, just save it. If nobody says anything, then it's not a terrible idea. That's great. All right. And the second thing, and also addressing, Sebastiano mentioned this earlier, I think it's very important. It's just we cannot do this due to technical limitations also. So in my opinion, I believe the having great performance, that's amazing, right? But at what cost, right? And the cost being performing an inference, right, requires resources doing so. Right, and so if you want to create a system that can automate, that can label thousands of issues, in a second, whatever. Well, obviously, we need to create a model that can also do so with reasonable resources. So, what do you think if in the next year, not only the performance metric will not just be the F1 score, but also we adjust for inference performance in some way?
Yes, maybe in that case, that would be more variety in the models used. Maybe not just BERT, which probably would be a lot slower, but maybe some other models. Of course, with that amount of data, if you want to use, let's say, traditional machine learning, such as an SVM or decision tree, it would be harder to train it. And so there are some problems to address.
It's a trade-off, right?
Yeah, exactly.
All right. Nice discussion. I wish we had more time to discuss. I mean, this is really interesting, but we don't have time. So we thank again all the participants and the audience for sticking here and listening to the talks. And so thank you very much, everyone. And let's have a break let's have a 7 minutes break. We'll come back at the 30. I don't know what time is in Europe, but here is 11:23. So until
here is afternoon, basically the opposite.
There you go.
You're very fresh. Hopefully.
Yeah.
Hopefully.
All right. I'll see you in 7 minutes.
Okay, Andrea, you shared. Oh, great. Super.
Okay, guys, can you see my screen?
Yes, Andrea.
Okay. Thanks. Now we go for the next section, in which we have 3 full papers, 1 position paper, and a short paper. The first paper will be on the evaluation of natural language parsing models for software engineering. The second paper will be on transformer-based machine learning. The third paper would be on neural machine translation. The fourth paper is about systematic literature reviews in using deep learning based language models. And the final paper is about story point level classification by text level graph neural network. So I leave the stage to Mali for her position paper.
Oops. Can you hear me and see the slides?
Yes.
Okay, good. Hi again. For those of you who weren't in the previous session, my name is Maddie and I'm a postdoc researcher at the Technical University of Delft in Netherlands. In this presentation, I will talk about our work on evaluation of natural language processing-based models for software engineering. This is a collaboration with Matin Nidi, who is an alumni of software engineering from University of Tehran. Okay, I think that I can say that all of us here are interested in natural language processing, or we have devised our own NLP-based model for software engineering tasks. These tasks can include generating code based on a piece of text, completing code in IDEs, translating from one piece of code to another, automatically fixing bugs, answering questions using bots or on Stack Overflow, documentation, and test case generation. So considering the diverse application of NLP models in software engineering, how are these models being evaluated? This is the question that we aim to answer in this work. To answer this question, we performed a systematic literature review. The protocol we use here is based on the information on the right side of this slide. We define our search phrases as natural language processing code, source code, and evaluation. We included primary studies that were peer-reviewed and written in English. These studies should have been published after 2017. And these are the top journals and conferences that we included in our literature review. At the end, we reviewed 104 papers, and what we got is that there are 2 main approaches for evaluating NLP-based models for software engineering. One is automatic evaluation, and the other is manual evaluation with the help of human participants. For automatic evaluation, we identified 3 types of main techniques that are usually evaluated using automatic evaluation. The first group is techniques that are used for classification. Studies such as issue classification, as we saw in the previous session. These studies are evaluated using standard evaluation metrics such as precision, recall, and F-measure, and they are pretty straightforward. The second group are recommendation lists, techniques that provide or recommend a list of suggestions. In this group, studies are taking into account the rank of the items in the recommendation list using metrics such as mean reciprocal rank, MRR, or they would use mean average precision or top N for considering rank and the position of recommendations in the recommendation list. And finally, there is the third group, which is the techniques used for generating text or code. And for both of them, software engineers mainly use measures that are being used in the natural language-based domain, which are BLEU, Meteor, Rouge, and metrics such that. For manual evaluation, we saw different metrics. manual evaluation is based on human expertise, and you can see a list of manual metrics here. This isn't a comprehensive list, but we are completing this study and we are adding to these measures. But one notion that I wanted to talk about here is that, for example, the first measure, usefulness, is used in many studies, but it's defined and used in different ways. For example, one study would use it as how easy is it to read and understand the output of a model for end users. Another would define it as how smooth, human readable, and syntactically correct are the outputs. So you can see that this specific measure is being defined and used differently in different studies. There are other metrics that are termed differently, but they basically mean the same thing. For example, naturalness, expressiveness, readability, and understandability. All of them are defined similarly, but termed differently in the literature. And to compare this, we can say that automatic measures provide a more objective evaluation for assessing these models. They are faster and they are easier. But on the other hand, manual evaluation can be a bit more informative because they engage participants and they depend on their knowledge, so they can be more informative. But they are a bit harder to obtain. And they are also based on the biases of participants and the biases of the researchers themselves who had defined these metrics and defined the experiments. So all of this should be taken into account when we want to evaluate a model. There is also an interesting recent study by Roy and colleagues on the correlation between these measures in the code summarization field. And they actually used the help of more than 200 human annotators and studied the correlation between the result of automatic measures for code summarization with human assessment. And they claim that less than 2 points of improvement in automatic measure doesn't correlate with human assessment in significant improvement in human assessment. So the challenges and future work on this direction would be that we believe for evaluating these models correctly and to have a holistic view of a model's performance, we should have both of them. But of course, they are both applicable or viable in different cases. Regarding the manual evaluation, there are conflicting, ambiguous, or overlapping metrics. And this should be addressed by the community. And for that, we suggest that we come up with an evaluation framework that everybody can refer to and use when they want to evaluate their models. And one last suggestion would be to devise new metrics that are specific to the source code, that take note of the syntactic and semantic of source code compared to natural language, and take all of this into account when assessing a model's performance. For more information, you can find our preprint. We are currently extending this work and we are adding more studies to this work. And we would be happy to get your ideas and input to improve this literature study. That was for our study, and I would be happy to take any questions.
Thank you, Mali. Any question? I have one. Are there software engineering specific needs in the evaluation of NLP models as compared to other files?
Mm-hmm. You mean the difference between software engineering and other domains?
Other fields, yeah.
Yeah, exactly. This is the fact that source code compared to natural language has a strict structure, and or maybe say as an enriched structure that we can make use of. And the outputs, for example, in the case of a code completion task or a code generation task, it needs to have synthetically correct order and be compilable, for example. So there are differences with natural language. Yeah.
Okay.
This is only one example.
Yeah. Yeah, thank you. Other questions?
So I have a question. So do you think that empirical standards that are already kind of out there aren't good enough for measuring the effectiveness of, for example, data collection for machine learning models that we use for software engineering? So do you think that we need new, like, empirical methodology or qualitative analyses in order to solve these issues?
For data collection or for assessing the models, because I think that the methods that we have already, they are good, but we need to make them specific to software engineering, and we also need a standard framework. For example, when we have different software engineering tasks, such as code translation, what measures or manual measures should we take into account compared to when we are developing a code completion model?
I see. Okay. And do you have any what would you say that could theoretically look like in the future?
The framework itself, you mean?
Yeah, a framework per se. Yeah.
This is what we are currently working on, and we are at the very beginning. We want to first define the tasks that would encompass the software engineering domain, and maybe I can envision it as a flowchart, the most basic form that you would refer to. This is a supervised task or is it an unsupervised task? If it's a supervised task, what tasks do I need to focus on? And for that task, what measures do I need to use for my evaluation, and how those measures are defined uniformly across the field? I hope that.
Okay. Yeah, no, that's good. One more quick question. So do you think that this kind of framework would have to be different for different subdomains? So for example, would the framework work for if we're doing code translation and identifier recommendation and code summarization, or does each of those individual tasks require their own individual treatment?
I think regarding the automatic measures, they are pretty straightforward and they can be used in the commonly. But for manual, I would envision different measures. But it depends on the task themselves.
Okay, thank you.
You're welcome.
Okay, thank you, Marie. We can go on the next paper. Please stop sharing, Marie. Okay. And the second paper is identification of intradomain ambiguity using transformer-based machine learning. Ambarish will present paper.
Yeah. Hello. Can you see my screen?
Yeah.
Okay. So, hi, I'm Ambarish, and in this presentation, I'll brief you about our work identification of intradomain ambiguity using transformer-based machine learning presented at the NLBSE 2022 workshop. This work was done in collaboration with Professor Dr. Arpit Sharma from the Indian Institute of Science, Education and Research, Bhopal. The motivation behind this work can be divided into 4 parts initially. Extensive documents, requirement documents or requirement documentation at times can be extensive, and large documentation which the requirement engineers or the software engineers need to go through. And while going through these extensive documents, these software engineers come across several ambiguities. Now, what are these ambiguities? Essentially, when these requirement documentation consists of a lot of domains or intradomains, there might be words that have different contexts, and these words are essentially termed as polysemous. And when keeping a track of these different contexts, the author can of the documentation can either provide a glossary with mapping of every context of a word associated with its different contexts, or essentially the reader can start maintaining a manual glossary where he starts inputting a word and then all the context associated with it. But the problem with this brute force approach is that when the documentations are huge, or essentially when you want to review multiple documents, keeping a track of this huge glossary becomes quite a difficult task. And hence we need an intelligent solution which automatically tackles these ambiguities and also handles new vocabulary that the documents include, and is also adaptive to different languages. Essentially, if the documentations are, for example, say in Dutch, we need the model that is adaptive to Dutch and not only to English. So with this motivation, we design an approach. But before we move to our approach, we should understand how the success of a software product can be defined. So essentially, a software product can be said to be successful if it meets the expectations. And Nuseba and Estabrook define that the degree to which a certain software system meets the purpose for which it was intended can be taken as the main measure of success in software engineering. And hence requirements elicitation becomes a foundational task, because if elicitation is done improperly, then the expectations will not be matched by the product and the whole development cycle will not be termed as successful. When doing this elicitation process, the requirements engineer usually does it at his or her own office, or can carry out at the stakeholder or the client's place. But at times it happens that the client does not have enough resources to provide domain experts for the elicitation process, and the engineers have to do it themselves based on the domain knowledge they have. And this leads to the problems that I stated before. But before we move to our approach, let us review what has been done in the past. So in 2012, Alessio Ferrari and Stefania Nessi, they provided a graph-based approach to tackle these ambiguous terms in a large corpora or a corpus. But the problem with this graph-based approach is that when we are dealing with a huge documentation and a lot of words, the interpretation becomes difficult. Other than that, two words might have many similar words that are similar to them, but they are totally used in a different context. I'll show this example in later slides. And essentially, just having a representation of the similar word does not help our case. At times, having sentence representation also helps and is very essential to understand the proper context of the word. Then, as time passed, we had word embedding based solutions to tackle this ambiguity, but the word embedding based solutions are also not foolproof. The biggest problem these algorithms face is that they make use of a static word embedder. And the problem with using a static word embedder is that every word vector is assigned the similar vector representation throughout the corpus. So, for example, when we compared the word similar to the word concrete above the threshold of 0.45, which we defined in our experimentations, we found out that the word concrete was similar to the words like steel, cast, masonry. But when we did it with BERT, we found out two totally different contexts in which the word concrete was used in within the same document. And as you can see on the slides, in context 1, concrete is used in the context like, say, a concrete argument. And in context 2, the word concrete is referred as a building material, essentially. And as I said earlier, these models should be adaptive to out of vocabulary words, which word2vec is not. Fasttext takes care of this thing, but then again, there is a debate on the number of n-grams and character n-grams that we need to select. So we essentially propose a unsupervised based approach, and our approach can be divided into 4 phases, as you can see on the slide. In the first phase, that is the Wikipedia crawling phase, we essentially crawl two corporas. The first corpus is a computer science corpus, and the second corpus is a computer science corpus plus 7 other domains, as you can see on the slides: ceramic, petroleum, and all the other engineering domains that we stack together sequentially and make a one big corpus out of it. We parse the Wikipedia tree in a breadth first search manner, where every node is basically the subcategory, and the leaves are essentially the number of pages, and the total number of pages for every domain was restricted to 10,000. As you can see here, the words that occur in every domain are quite large, and hence this problem of contextual disambiguation for a particular word, it explodes, as these words might have a varying frequency throughout the corpus. Then we perform data pre-processing. Data pre-processing is just a simple process where we make sure that every sentence is of the length 512, as it is the requirement for the BERT base encased model. And we tokenize these sentences from our documentation in the length of 512. And we remove stop words, the normal stop word removal, but we pretain certain words like C++, C hashes, certain characters that essentially capture the context of the computer science domain. And we finally create a sentence list. Next, we move on to extracting the contextual word embedding. Now, this phase is the most important phase of our entire approach because when we have to disambiguate a term, we first need to define the ambiguous terms in the corpus. For our analysis, we did a frequency analysis and captured the top K most frequently occurring words. And the intuition was that in how many different contexts are these most important words present in. So once we have the set of ambiguous terms, that is the capital T, we can select any term small t out of that set. And we sample essentially the number of sentences in which that word T was used in, and pass it through our BERT base encased model. Now we store every n. Now say the sampled word small t was used in n different sentences in the entire corpus. We sample n sentences from our initial sentence list and pass it through the word base encased model and capture each word embedding of the word small t, and essentially store these n occurrences in a label list. For traceability purposes, we keep a label list and the sentence list, where the sentence list is essentially the sentences in which this small target term T was used in. Once we have n distinct embeddings of this target term T, we create a similarity matrix by computing a cosine similarity between one word and all the other occurrences of that same word. Essentially, we compute this similarity by calculating the cosine similarity, because in higher dimension, the cosine similarity is just the dot product between these two vectors, and which gives a real capturing sense of the similarity between these two vectors. It's a diagonal matrix where the diagonal elements are 1, as the similarity between the vector itself is 1. We then feed this similarity matrix to a k-means clustering algorithm and obtain k different contexts from the algorithm. Now, the number of context bucket is essentially the number of contexts in which the target term T was used in. This is an important process. Now, k-means algorithm is a supervised algorithm, and we need to essentially define the number of optimal k value, or the cluster value, for which we need to cluster a similarity matrix. Now we compute this optimal k value by computing the minimum WCSS score, and this k value is selected for the cluster number for which we get the least WCSS score. When we have the context buckets, the output is essentially k files, that is k text files, where each file consists of the words, the sentences, and the most similar words to the related word. I'll make this more clear by taking an instantiation. If you look at the context buckets, let's look at the context bucket C1. In C1, let us say that the term T was used in m different sentences, and there are 1 to m sentences in cluster 1. So for cluster 1, we take the term T1 to Tm. The word T1 is then printed. The word T1 is printed. The use of that word T1 in that sentence is printed, and then we vectorize all the words in that context and compute the similarity between the word T1 and all the other words present in that context, so that we capture the essential contextual implication of the word T1 in the context cluster 1. And similarly, we do this for all the other K contexts. Now, these are the results of our algorithm. As you can see, the word cell in context cluster 1 represents as a biological cell, and it is quite evident from the the most similar words in that context clusters that we get, and the sentence representation that that particular word cell has in. In context cluster 2, we see that the word cell is used as a mobile phone. And from the sentence itself, it becomes very clear. And from the most similar words, it is quite clear. And similarly, in context 3, the word cell is used as an element in data representation, like a cell of a table or a row. We then move to the multi-domain corpus, the second corpus that we made. And the idea is that essentially if a word is being captured in certain contexts in the CS domain, like for example, 2 contexts in CS domain, if the same word captures multiple contexts in a multi-domain corpus, then we essentially say that our algorithm is robust. Now here I would like to show these examples, because as I said earlier, for the graph-based techniques, that just seeing the context words does not define the entire meaning, because if you see the first and the second occurrence of the word bank, you will see a lot of similar words essentially when we looked at the output files. And the first context implication of the word bank is for sure. And the second context implication of bank is like a steep slope. And as most of these words were used in essentially a more similar fashion or in more similar contextual manner, even though their implication is different, the similar words that they had were quite similar. And hence our approach was quite robust in delineating these 2 instances of the word bank. Similarly, in context 3, we have bank is being used as a financial institution, which is the most common interpretation of the word bank. And in context 4, we saw that bank was used as a storage unit, like a blood bank or essentially a power bank for storing charge. And we conclude from these experimentations is that what we now have is an unsupervised approach that, given a requirements documentation or any corpus, can capture robustly multiple contexts of the same word when we have multiple domains that are present or levels of domains that are present. And by using k-means clustering, we can actually capture the contextual information around these words. Then we also applied our technique to a CS specific corpora and also a multi-domain corpora, which consisted of 8 different domains. And that was kind of a validation step for more or less of a validation thing for our entire approach. But there is still some work that needs to be done. First of all, our current approach is that we are aiming to prepare a tool that can be used by hands-on engineers. When they have requirements documentation, they can just select any n number of terms and they can start disambiguating them using this tool. Then essentially we need to experiment this, that all the results that we got were using the BERT base uncaged model, and that, as said earlier also in the workshop, that training the BERT model on a domain specific corpus might yield quite different results, and we need to investigate if these results are an improvement over the current results we had. And also we need to find a method to robustly validate the results that we have, because it's an unsupervised model. And third, our approach can be applied in detecting intradomain ambiguities in crowd. Can it be applied in intradomain ambiguities in crowd-based RE? So this is the end of my presentation. I thank you very much for listening patiently. Following is my Twitter handle and my email. If you need to contact me regarding questions or any doubts about the presentation, or you would like to collaborate for future works, yeah, it'll be great. So thank you very much.
Thank you, Marish. Any questions from the audience?
Yeah.
I have a question.
Yeah.
Did you perform any quantitative evaluations beyond qualitative ones?
The only quantitative evaluation that we performed was measuring the intercluster distances between the context clusters that we received, and to see how much overlapping these clusters had, because to essentially say that context cluster 1 is different from context cluster 2, we need some quantitative method to define that. Other than that, we did not perform it because we did not perform inter-rater agreement, because the documentations are quite large. These corpuses, they contain like 6,000, 7,000 pages, and going through all of the sentences is quite an extensive task. So we still are researching upon methodologies that can surpass these manual techniques. But essentially, if we would like to have a quantitative evaluation, we can always perform inter-rater agreement or coherence kappa on our documents that we generated, and then we can quantify if the results were expected or less than expected, essentially.
Okay, thank you.
Yeah.
Other question?
So did you take some Did you make any effort to see what the possible weaknesses of this model would be? So you found that you were able to disambiguate some of the terms that have some of the polysemy that are kind of blatant in these data sets. Was there any type of word or any type of data that you had trouble with categorizing or classifying correctly?
Yeah, yeah, it's a good question. Essentially, yeah, we did face this problem. First of all, this problem occurs is because words that occur less frequently. Say if you have a documentation of 10,000 pages and a word is occurring just 10 times, then what happens usually is that the k-means algorithm by its nature always predicts two clusters. So that is wrong, because if the word has been used in one context, then we should essentially get one context cluster. So we are still researching upon robust clustering techniques to tackle this problem. Other than this, if the frequency is low, what usually we observed was that the number of clusters or the optimal k value predicted by the k-means algorithm was high, which went to around 5 to 6 clusters, which is quite rare for a word to be used in 6 or 7 different contexts. So yeah, essentially. Plus another problem that I would weigh on would be using too much, using sentences that are too much domain specific. Like if we have a code excerpt into the model, then I think the model would be a bit susceptible to such kind of words, and the context disambiguation would fall all over the place.
Gotcha. Thank you.
Yeah, thank you.
Okay, thank you, Ambarish.
Thank you.
I think that we can go. On the next paper. The next paper is Can and T Understand Me towards perturbation-based evaluation of NMT models for code generation. The presenter is Simona De Vivo. Simona, I think that you can, okay.
Can you see my slide?
Not yet.
Now?
Not yet. You should use the share button in the right corner of the MST. We don't see you anymore. Okay.
See?
What's the problem, Simona?
Now you can see.
Yeah. Okay. Please go ahead.
Hi everyone, my name is Simona Devio and I attend the first year of my PhD at the Federico II University in Naples. The goal of my research is to leverage AI techniques to develop a solution that can protect, identify, and respond to cybersecurity attacks through an infrastructure monitoring solution that is automated, low energy, and low in processing resources, effectively fitting into the concept of sustainable cybersecurity. I'm going to present the paper Can NLP Understand Me? Toward the perturbation-based evaluation of NLP models for code generation. Neural machine translation techniques are becoming increasingly popular in many domains, including software engineering. An interesting application of NLP models is the code generation task, which consists of an automatic translation of intent and a comment in natural languages such as English into a snippet of code written in a specific programming language. The main problem for this model is the difference between the intent in the corpus that is usually two values and the language used by programmers that to comment on the code. In the table, there are three examples of intent snippets in which we observe a description that takes more time to be written than the effective line of code. Moreover, we must consider that the description could be formulated in different ways or be more or less detailed, but still be valid. Therefore, these models should be able to cope with the variability of the input and be robust to the ambiguity introduced by natural language. And considering this, we wondered what the most correct way was to evaluate the robustness of NLP models in the context of code generation tasks. The contribution of this paper includes the identification of a series of perturbations suitable for code generation tasks, the identification of a series of metrics adapted to evaluate the robustness of the model, and which accounts both the presence of noise and that the target language is a programming language, and an in-depth analysis, in-depth experimental analysis. The experimental analysis was carried out using the Shepherd dataset. The model used for translation is a sequence-to-sequence model that uses the attention-based mechanism and whose architecture relies on an encoder-decoder paradigm. A central approach to assessing the impact of noise on translation is the robustness testing, or evaluating performance in the presence of adversarial inputs that are inputs obtained by introducing small perturbations to the original ones. To this end, a crucial step is to identify a set of non-random perturbations that can simulate the ambiguity of natural language and that are suitable for assessing the robustness of the models. The first type of perturbation we identified is called synonyms, which is the replacement of words in text set with synonyms not seen by the models during training. We selected synonyms from the set of neighbors of a word in the word embedding space, and we applied constraints on substitutions to increase the level of similarity. These constraints are distance between word embedding, best for a metric that also consider the context of the sentence to assess the similarity, and the part of speech target to ensure that only terms with the same rule in the sentence are substituted. In the table, there are 3 examples showing how the meaning of the sentence changes with and without constraints. By preserving the intent without constraints, had has been replaced with include, so maintaining syntactic correctness, but moving away from semantic similarity. Using constraints, on the other hand, had has been replaced with the some, that also maintaining semantic similarity. To avoid altering the meaning of the sentence, we avoid replacing words that are particularly significant in the context of assembly programming. To find them, we compare the most frequent words in an assembly programming book and a narrative book. The 15 most frequent words in the assembly programming book, including register names and words such as variable and function, never appear in the narrative book. This fact shows that those words belong in the context of programming. The other type of perturbation targets the relevant information within an intent or action. It describes the specific goal or value of this action and so on. And in the light of this consideration, we can identify 3 subcategories: omission of information relating to the action or verbs, omission of information relating to language or keywords, and omission of specific value or names of registers and functions. The example shows the effects of this perturbation on an intent. In the first case, the verb store is removed. In the second, the keyword register, and in the third, the register name. We know that the intent does not lose its original meaning because it is all implicit information. The metrics identified to assess robustness compare the snippets produced by the model and the reference snippet. We distinguish between automatic metrics, which analyze similarity at character and word level, and manual metrics, which also account what the snippet actually does. In particular, the automatic metrics, however fast and reproducible they may be, do not consider two fundamental aspects. That is a matter of code generation, so one must assess the syntactic and semantic correctness of the generated snippet and the presence of noise, so that an output may be correct with respect to the perturbation, even if it is not correct with respect to the original version. We performed a series of preliminary experiments to assess the ability of the model to tolerate noise and still produce accurate results. We evaluated the robustness of the model using 3 different types of perturbation, and synonyms with constraints using backscore and POS tag. We applied a transformation only when the synonyms chosen as a neighbor in the word boundary space and the original word have a backscore similarity greater than 0.85 and the state POS tag. We empirically chose a high value for backscore similarity to introduce the divergence in an intent without losing the original meaning. We randomly substituted the 10% of the selected words within a single intent, ensuring that at least one word is equipped with the synonym in each intent, and omission of language action-related words. We remove the verbs from each intent in the test set using a POS target, and omission of language-related words, in which we remove the assembly programming language-related words from each intent in the test set. And we use the text related words with the synonyms and enforce the constraints and the POS tagging model as a part of speech tagger. And we perturbed all intent in the test set while we did not add any noise in the training set and in the dev set. To feed the model, we used the assembly dataset released by Ligoria Store to automatically generate assemblies from natural language description. The dataset contains 3,715 unique pairs of assembly code fragment intent in English, and the line of code in the dataset were used in real software exploits and were taken from exploits databases, books, etc., while the English comments were made by different authors. More information about this dataset can be found in the paper presented in Israel. In this table are shown the results obtained by experimental analysis with automatic metrics. As automatic metrics, we used the view4, the exact match accuracy, the edit-based metric, and the SCS-based metric. Among the types of perturbations, the use of unseen synonyms with constraints affected the performance of the model, the least which proved the largest when dealing with the word synonyms, and also to the highest best score similarity set as a constraint. Removing explicit information from the intent, on the other hand, negatively affected the model's prediction. In particular, the removal of action-related words resulted in worse performance in terms of exact match accuracy, AD-based metric, and ACS-based metric, while the model shows the worst view for when dealing with the removal of language-related words. As regards to the manual metrics, each author undertook to evaluate both syntactic and semantic accuracy for each fragment predicted by the model. The table shows that the use of perturbation does not have a negative impact on the model's ability to predict syntactically correct code fragments. Even better, the removal of action-related words slightly increased the performance of the model's syntactic accuracy. Through an in-depth analysis of the model's output, we found that removing the verbs led to the prediction of code fragments that are syntactically correct, but led to the most significant growth in performance in terms of semantic accuracy. While the use of unseen synonyms and removal of language-related words negatively affected the semantic accuracy of the model, but the drop in semantic accuracy is more limited. In particular, the table shows that the semantic accuracy of the output obtained when language-related words are omitted is close to that of the original test set. We conducted a t-test which showed that only the results for the perturbation, unseen synonyms, and action-related words show a statistically significant semantic difference. All other results did not produce any statistical evidence. In conclusion, I can say that we addressed the problem of evaluating the robustness of NLP models for the code generation task by proposing a set of perturbations and metrics to assess the impact of the models when dealing with different inputs. We performed a preliminary evaluation of the sequence-to-sequence model in assembly code generation from the natural language description, and showed how different perturbations on the input affected the performance of the models. As a significant result of this preliminary evaluation is that in the generation of assembly code from natural language, the NLP models can handle the use of synonyms in intent, and thus different ways of describing the code by different users. And it's very relevant to non-explicit information about language-related words such as keywords, and is greatly affected by intent where action are not explicit. As future work, we propose to extend the robustness evaluation to different DL-based architecture, and we are also investigate different solutions to make NLP models more robust, and we encourage the use of adversarial training or injecting perturbed input into training data to increase robustness, and the development of solutions that help models derive missing or implicit information from the program context. Thank you all for your attention.
Thank you, Simona. I have a question. Can you provide more details about the manual metrics, how they are computed?
Yeah, as manual metrics, we use different metrics that we can see here. Syntactic,
yeah, the process, about the process that you used for...
Once we obtained the results by the models, we observe the obtained results and the reference, and manually we see if the obtained were equal or semantic and syntactic correct with as the reference. And if it was correct or well done, we in it with 1 or 0 if it was not correct. And in this way, we made some decisions.
Okay, did you use multiple raters for doing this?
Yes.
Okay, thank you. Any other question? Yeah. Another question is just a curiosity. Did you try to explain the rationale behind the different perturbations? Why different perturbations lead to different results?
We studied the ambiguity of natural language. So we suppose that a user can forget some words or use some synonyms. So we chose the major used ambiguities of natural language to make perturbations.
Yeah, I think that it was a quite expected result that removing the action you could lead to a very low results.
We consider that also someone can do some mistakes, so we provide a large range of perturbation of natural language.
Okay, thank you. I think that we can go to the next paper. The next paper is supporting systematic literature reviews using deep learning based models. The presenter is Manu.
Hi, everyone. Can you see me?
Hi. Not yet.
Maybe?
Yeah.
Okay.
Now we can see the screen.
Okay.
Please go.
So hi everyone, I'm Manoj Borkers. I'm a student at Otto von Guericke University from Magdeburg, Germany. And today I'm here to present mine and my co-authors' work on the paper supporting systematic literature reviews using deep learning based language models. So this is an exploratory work on supporting systematic literature review using language models. So So to give a little introduction about systematic literature review, it is the entire process of identifying and then interpreting, evaluating, and summarizing all the relevant research or all the relevant documents relating to a certain topic area or a research interest or a certain whole topic itself. So I think today in the keynote, like Professor Dennis mentioned, there was a systematic literature review of using deep learning based models in software engineering domain. It covered certain insights into the usage of deep learning models in software engineering and provides certain statistics about various results that was gathered. So basically, it is an evidence-based practice where the intention is to reduce bias and unintentional repeat in research and gather a study over multiple primary studies. So there are three main phases of SLR. So first is the identification or the planning phase, where the entire need for a review is identified, and then there are certain protocols defined, whether on certain exclusion criteria, inclusion criteria of certain research into the relevancy and so on. And then next is the conduction phase, where this process is identified, where the relevant research is identified and various studies are selected. The results are assessed and extracted and synthesized. And then next is the reporting phase, where right from the planning phase to the conduction phase, whatever is there is summarized in the form of a report. So what makes an SLR challenging is, as we all are researchers in different fields, we know that the number of scientific articles are increasing every year, and therefore manual identification, which is through the unbiased selection process, becomes more challenging and time consuming. And often, since it's a human-based, human involvement process, it's often labor-intensive and prone to errors. So there's always been this need for full or semi-automation of the conduction phase of the SLR process. And there are various tools that have approached conduction phase of SLR, using various classical techniques. Certain tools such as Slurp Start SLR tool make some of these tools are for the entire stages of the SLR development, but these have certain complex installation procedures or collaboration failures with various researchers and so on. And then there are other tools such as Revis and Project Explorer, which make use of certain machine learning or semantic techniques wherein they focus on certain approaches and provide mapping between documents. But the main primary focus is always on study selection and data extraction. So the common drawbacks that we noticed in all these techniques is, or that is often with any machine learning or text mining techniques, is that even if you take TF-IDF, which we've considered it as our baseline in our work, or bag of words, or anything of that matter, where the positional information of the words of the text is not considered into account, and obviously semantic relationship between words is not captured over long sequences. So that is our motivation, basically, to explore various deep architectures to semi-automate this conduction phase. As you all know, we are in NLP, natural language processing is experiencing an ImageNet kind of movement where deep learning methodologies are outcompeting certain various statistical and linguistic approaches in several tasks. And like I said, in order to fill the drawbacks of certain ML and text mining approaches, wherein the contextualized meanings is not taken into consideration, the positional information is not taken into consideration, and also the relationship with respect to words or longer sequences is not taken into consideration. And now more than ever, there are a lot of pre-trained language models that are available, which I think all of us throughout the talk have talked about various language models that we've used. So the goal of the project is to integrate this learning from various contextualized document representations, which can help us in identifying relevant research and therefore accelerate the conduction phase of the SLR process. So our architectural setup and design is mainly divided into three phases. That is the embeddings module phase, wherein we capture representations at different fragmentation levels of text, such as word, sentence, and paragraph. And then next is the weighting scheme module, where we've designed a scheme to weight the embeddings which are in alignment with the SLR search string. And then next is the clustering module, where we group embeddings to form relevant and non-relevant clusters. So to talk about the document embedding module, so like I said, this is a conscious decision to experiment or fragment the data into different levels of text so that we could know what level of text we get actual representations that can be useful for our relevant clusters. So we divided into word level, sentence level, and paragraph level, like I said. And then for the paragraph level, we take the whole chunk of text as a whole. And for getting document level embedding, we calculate embeddings per sentence or per words, and then average it over an entire set of words or entire set of sentences for that particular document. And for the document embedding module, we've used specifically two models, that is the BERT-based case and the sentence BERT in the form of paraphrase distilled robota model. First of all, BERT-based case, because on exploring the data set, we found that the casing was important with respect to certain abbreviations or certain terms wherein the casing was appropriate. And also these BERT and sentence BERT specifically has been trained for mass sequence presentation, and then for next sentence prediction, and paraphrase is completely on sentence based on Siamese network transformers. So since we are fragmenting the data on different levels, it was important for us to use these two models. And for the weighting scheme module, what we do is we take either the search string, that is which contains the certain keywords for the particular systematic literature review, or we construct a TDF-IDF keyword list which contains of important words belonging to the entire corpus of the systematic literature review, or this can also be further extended to containing similar contextualized words as a list as a whole. So based on this list, what we do is this applies to only sentence level embeddings, wherein for each sentence in the document, we have a tracker that tracks the matching words to the search string or the TF-IDF keyword list. And then we add this embedding weighted, we add this weight while we calculate the embedding. And then we obviously normalize it based on the length of the words for each sentence or the length of the sentences for each document. And so this is what we get. So for each sentence, we calculate the embedding, and then for each embedding, we have a weight, which then we get for the, when averaged over, we get it for the entire document. So for the, as part of the clustering module, we've used k-means. So as you all know, clustering module is, clustering is basically an unsupervised technique to group things together. And k-means is one, we wanted to keep it as simple as possible, although we've experimented with different clustering techniques. K-means was appealing because of its simplicity and also its adaptation to new instances of the data set, or when this corpus gets bigger, and so on. And in order to understand the appropriate number of clusters, which is the k value which is required for k-means, we use the elbow method provided by this neat digital library, which helps us to determine the number of clusters. So our data set is basically Scopus extracted documents for a particular search string or topic of interest. So like I said, the initial result set can contain a lot of documents ranging from 100 to thousands of documents. And for this particular data set that we've used, we've identified primary studies which are labeled as relevant for the relevant research and non-relevant for the rest of the documents in the study. For example, this is one of our data set where this is a systematic literature review on bat smell detection using machine learning techniques. So when you search on Scopus, or the key search string for this is basically code of bad and smell and artificial intelligence or ensemble learning. Basically, you use a combination of various operators and keywords to identify all the relevant research pertaining to this particular search string. And so according to this systematic literature review, the number of initial research documents identified were 153, and primary study out of them manually identified as were 12. So out of all the papers that were identified for the documents, we mainly select title, abstract, keywords, and then provide our labels of relevant and non-relevant based on the relevance to the systematic literature review. So why specifically these was because, one, we were concentrating on extracting as less information as possible, so that to see if the model can learn on less information, that is just the title and the abstract. And we only kept those data where the information was complete for all three of these categories, or mainly for the title and abstract categories. And our next data set was systematic literature review on automatic software refactoring. This is again a systematic literature review which was published in 2019, where the number of initial documents identified are 174, out of which the primary study set is just 9. So as you can see, there are a lot of documents that are part of the non-relevant set as compared to the relevant set. And again, we identify title abstract keywords and provide the label of non-relevant and relevant. So evaluation is basically mainly qualitative evaluation in terms of the identified documents, and then comparison with the manual study on the systematic literature review. And our baseline, one of the approaches that we could compare it to is the TF-IDF approach, which is one of the standard SLR classical approaches. And for quantitative evaluation of our clusters form, since ours is an unsupervised learning technique where we get the embeddings and then cluster on them based on a certain weightage scheme, we use false malus index as our qualitative evaluation metric. And as I said, there are different variants that we have tested against. First is the model variants, that is the BERT and the SBERT, and then the weighted and the unweighted schemes and various fragmentation levels of the text. So for the evaluation metric, like I said, we've used false malus index. This is generally a cluster-based metric where we can use when the ground truth labels are known. So basically, it provides a geometric mean of the pairwise precision and recall. And so here, true positive actually means the number of points that are identified as part of both the clusters in the true labels as well as in the predicted labels. So this takes the cluster into account while calculating the pairwise decision or the pairwise precision and the recall features. So this is our results. These are our results on the first data set, that is the SLR on bad code smell detection. So just to introduce the various parameters that we've measured on, first is the models that we've used. That is the various variants. UW means the unweighted one and the W means the weighted one, TF-IDF as a baseline. And paragraph, SBERT paragraph is just to work it on the paragraph level. And again, different levels of fragmentation. We have taken title and abstract together as a chunk of text where, again, based on the fragmentation, we break them down. And correct PS is the correct primary studies identified. For example, here 12 of the primary studies are manually labeled as relevant, and then out of them, how many we have identified. FMI score is the false malus index score, where value of 0 is very dissimilar and value of 1 is highly similar. And additional documents, this was important because often with various techniques, we can cluster similar documents, but what happens is there are a number of additional documents that are identified as part of the same cluster. So it was important for us to have a good balance in terms of the number of additional documents identified. And the last column is the clusters, number of clusters, which was identified by the elbow metric. So we measure our results mainly based on three things. One is the FMI score, the number of additional documents identified, the correct primary studies identified, and the execution times. So a good trade-off between all these criteria or these evaluation metrics will help us identify, helps us to identify that the SBERT weighted performs best in comparison to all other approaches. SBERT weighted is nothing but the approach of using sentence BERT with the weighted technique, and it identifies 8 out of 12 documents with very less number of additional documents identified as part of the relevant cluster, which is 10 in number in comparison to others, which are large number of documents. So our notion is that with the number of less number of additional documents identified, there's less laborious work to be done with respect to this. And similarly for the result 2 data set, although a different model performed better, in this case the SBERT paragraph, where again, when you consider the trade-off between various parameters that I mentioned previously, SBERT paragraph did identify 6 out of 9 documents with only 22 documents identified correctly. If you compare that to TF-IDF baseline that has identified 8 out of 9 documents, which is the highest in respect to this table, but it also identifies 104 additional documents, which may or may not be necessary as part of the relevant cluster. So the key takeaways from our exploratory analysis of using deep learning models to support systematic literature reviews was that, yes, majority of primary studies, regardless of the models used, majority of the primary studies were identified correctly. Please note that here we had our labels, but predominantly in a real-time environment, this will be an unsupervised technique where you identify the primary studies just based on the document set that you receive. And other key takeaway is that one of the settings with the deep language models. That was our main research goal, where to integrate these deep learning language models and extract information. So when you consider the trade-off, one of the settings always performs better. Although I would have liked to have better results on the performance of the weighted and the unweighted schemes, but it is very inconsistent, invariant of the model use. Perhaps with more data sets that we can perform these experiments on, maybe we'll have confined results on what works better. And always capturing embeddings at word level did not work at all. But at paragraph and sentence level, especially at paragraph level, we observed very good results. And yes. So some of the threats to validity that we see are that, one, when you extract certain documents from any tool with respect to a search string, obviously the results may change over a period of time as more scientific articles may be added, or some of them might not be valid to that particular search string anymore. And therefore, as results change over time, maybe we need to modify these cluster sets. And then for pre-trained language models, obviously, as we have more data set, it makes sense to fine-tune this model to a particular, say, a systematic literature review or an entire corpus of different systematic literature review or domain-specific data sets and its vocabulary. And obviously, we've spoken a lot about different language models that are available today. And one of the language models that was made aware to us from one of the reviewers was Scientific BERT, SciBERT, which I think which we were not aware of during that time, but would have done really well on our data because it is scientific text. And other model that I want to mention is one of the presenters mentioned during the tool presentation, wherein they use something related to specific to software engineering, if I'm right, as SciBERT or something like that, which also would have, I think, performed well on our data set. So yes, there are better language models available now, and then we would really like to see how these models compare on these systematic literature review and identification of relevant research. And obviously, evaluation, I think we've spoken about this today through various evaluation. Like there's a need for more development, especially in our case where we manually label these as documents that are relevant and non-relevant. Obviously, with the increase in the scale of the number of research documents that are available to a certain systematic literature review, then this needs more development. So yes, overall summary is that integration of deep learning architectures does help identify in primary studies and also accelerate the SLR process, conduction phase of the SLR process to be particular. And this we can get through the execution times that we took to perform all these experiments, which was not visible here, but I can share it. And yes, usage of pre-trained models, which is working like a plugin right now, makes the process far less tedious and saves effort and time, and capturing embeddings at paragraph and sentence level forms better clusters. So yeah, thank you for your attention, and yes, I would be happy to answer any questions if you have. Thank you.
Thank you, Manoj. Any question from the audience? Okay, I have a question. Did you compare your approach against n-gram-based representations? Because you said that bag of words representation suffer from the problem of the position of the word, but n-grams based representation do not suffer from this problem.
So with regards to the presentation, I was talking a whole lot of models together because I wanted to cover different various SLR tools and their approaches, underlying approaches. But with regards to your question, no, we haven't specifically experimented on using or comparing our results with the n-gram based model. But what I meant in general was that with regards to like say CBOW, wherein a certain sliding window is defined, and then you predict the context of the word or the next word or the target word based on the certain context. within a specific sliding window rather than a whole.
Yeah.
Yes. So that was my main point, but no, we haven't compared. Thank you for the question.
Okay. Okay, a suggestion for future work.
Yes, definitely.
Okay. Any other questions? Okay. Thank you, Manoj.
Thank you.
I think that we can go on the next paper. Next paper is story point level classification by text level graph for neural network. The presenter is Hang Fan.
Hello, can you hear me? Can you see me?
Yeah, yeah.
Okay. Let me share the screen. So can you see the screen now?
Yeah.
Okay.
Please go ahead.
Yes. Oh. So hello everyone. My name is Hung Phan. We are from Iowa State University, and today I will talk about story point effort estimation by text level graph neural network. So first, I will introduce about the research problem we focus on this paper. So in this paper, we focus on the problem of story point estimations. It is important. Is it an important problem, research problem in software engineering? So in software engineering, in agile development, you will create issues by you set the title, you set the description. And for the project planning, estimator will discuss and to unify the assigned story point for each software issue. So the input of the problem is the title and the descriptions of the software issues, and the output will be the assigned story point. And we can in this research we formulate formulate the problem as the problem of text classification in software engineering. So this problem is called story point estimation. So it will estimate the story point number of man per hour to complete each task or issue in Jira development. So the space of the assigned story point, they are integer, but they are usually follow the Fibonacci's number. They are usually set at 1, 2, 3, 5, 8, and maximum is about 100. And that is the reasons why we think about the possibility that we can formulate the problem as the text classifications and also the text regressions. So text classifications mean that from the input text you use a machine learning model to predict the label. While text regressions, you will predict the number assigned to the input text. So in this work, we want to test the ability of graph neural networks in story point estimations. So graph neural network is a very well-known concept and very well-known approach that appeared in natural language processing to solve many problems, including text classifications. So we use in this work we use a very famous engines called text level GNN in natural language processing. It appeared in 2019 to predict the rank of the story points for GNN using GNN text classifications. So we use the common baselines as the TF-IDF for vectorizations and the random forest for machine learning model for text classifications. And in the data set, we use the data set collected by Chokretikun et al. The data set called NLBSE. It is a famous data set of story points since 2016. It appeared around 2016, and it contains over 23,000 story points. So using term frequency inverse document frequency and random forest, in the step 1, we will use the input text as the concatenation of title and descriptions, and we apply a TF-IDF model to get the feature representations as the input vector for trainings. In step 2, we apply random forest for multi-label classifications. And this TF-IDF and random forest is the traditional approach for text classifications in natural language processing. And NLBSE also they also provide the deep learning approach for text regression purpose. But in this book, we focus more on the text, focus more on the problem as the text classifications means that we predict the rank of the story points instead. So let me go through the overview approach of the text level GNN in our paper. So given the inputs at the input as a title and descriptions, we will create a graph based on the text level GNN library, and we training the text level GNN library to predict the story point for new issues. So we relies on the graph constructions of text level GNN in natural language processing to conduct our work. So the idea of text level GNN is that it generates the graph from window with the specific size of the text. For example, if you have the window size as 4 here, so they will create a subgraph of forwards, and for each point, for each word, they will create an edge that connect the word together. So this is the default setting of the text level GNN. So and we think that there will be the risk of too many edges in the corpus because the vocabulary size of story point dataset is over 180,000 different words in the dataset. So to answer our concerns, we conduct 3 research questions. First, we compare the accuracy in classification of text level GNN with TF-IDF. Second, we also compare the ability in the regression problems. And third, we analyze the ability of optimizations in running time and graph complexity in text level GNN. So in the data set, we predict the rank of story points. So we set 4 levels: small, medium, large, and huge. With small will be the story point from 1 to 5, medium will be 6 to 15, and huge will be more than 40. So and here are the results for the research question 1 and 2. So we have the total accuracy of our GNN model is 78.63%, which is comparable but a little bit lower than TF-IDF and random forest using window size S4. And for the regressions, regression model, we use the mean absolute error. This is a metric that compare between the predicted score and the exact score. And we use we show that our GNN model achieved the comparable mean absolute error compared to TF-IDF and random forest. So, however, in research, we go into details of our approach. So we find out that our approach using text level GNN, it requires 25 minutes for trainings over 16 projects, while the TF-IDF and random forest only requires 4 minutes for training and testing the model. So that's why we conduct some analysis about the scale of the graph generated by text level GNN. We provide a strategy to somehow simplifying the graph, and third, we make win sensitivity by experiment by which vary the window size of the text level GNN. And let's see how it works. So here is the when we first we analyze the scale of the graph. we change the window size of the text level GNN, and we see that if we reduce the window size, the number of edge in the generated graph will reduce significantly. So yeah, and for the scale of the graph, when we extract from the training data, we see that the scale of the graph in the here 16 project of software engineering, they contains a lot of nodes and edge, and that's what cause the training time is it is very high. And we compare with the R8 dataset. It is a famous natural language processing dataset, and we see that the number of edge is smaller than the number of edge in the software engineering dataset. So we provide a very simple strategy to simplify the graph. In the text, we only keep the verb and the nouns in the 16 projects, and we achieve slightly higher improvement in the GNN model. And about the by simplifying the graph in the verb noun formats, we also reduce significantly the number of nodes and the number of edge. While we in some projects like data management projects, and we increase the accuracy. We do the sensitivity on the window size by we vary the window size from 2 to 100, and we see that here is the accuracy on the Jira software project, the Clover project, and the average of own projects. We can see that too big window size can cause the decrease in the accuracy. It possibility due to many non-useful edges in the constructed graph. It means that the default graph in natural language processing applied in text level GNN might not work well with the software engineering purpose. So in conclusions, in this research, we somehow we take a first footstep in propose a new mechanism of story point level estimations. Instead of converting text sequence to a vector representation for feature, we apply graph as a data structure. And by the experiment, we see that the text level GNN can achieve comparable accuracy with the TF, IDF, and random forest. However, text level GNN remain challenging related to the size of the constructed gap that impact the training time. So it brings room for improvement in the future works. That's conclude my presentation. So I'm happy to answer your questions.
Okay, thank you, Juan. Any question from the audience? I have a question. It seems that GNN-based approaches do not bring many benefits to the task the paper wants to solve. What is the advantage of the approach compared to previous approaches? What is the advantage of using GNN in this particular task?
I think the GNN can bring different representations and different strategy for representation. We have an analysis, and we see that almost all of the current research work on story point estimation, they focus on the sequence of text as the input, and it calls some model. It takes a very long time for training on the long text. So in this work, we provide a first step to using the GNN's the graph representations.
Okay.
Input text, yeah.
Okay. Yep. So you want to use GNN as a base representation for improving the accuracy of the classification.
Yes,
right?
And yes. And this research show that the default graph representations in natural language processing it cause challenge for getting accuracy. So that's why in future work we need to apply new graph representations that are suitable for software engineering purpose to improve the accuracy of the graph neural networks model. Yeah.
Okay, thank you.
Yep.
Any other question? Okay, I think we haven't any other question. So, thank you, Anne.
Thank you.
Now we can move on the closing. We are a bit late, but I will try to finish in the minutes. Just I'm okay. Can you see my screen? Is my screen visible?
Still loading for me. Yeah.
Okay.
Okay, now.
Okay. So these are the number of this new, this first edition of the workshop. We had good numbers, 121 registered participants, specifically for NLBSE. We had 37 total attending participants as peak. The peak, we reached the peak, I think, in the first session of research papers. We want to thank all of you for joining, for your participation in this workshop. Participation is essential. And I think that we managed to have a good interaction with all participants. So thank you. I want to thank Prof. Denis Pashivanic for giving a stimulating, enlightening, and instructive talk. I want to thank a lot Oscar and Raphael for the great work that they have done with the tool competition. They organized a very exciting competition and relevant tool competition. Thanks to our web chair for the hard work for moving the online. For moving online the workshop, because there were always problems to move workshops online. I want to thank the program committee members for, of course, for their support in reviewing papers. And what's next? Of course, we want to propose the same workshop. The new edition of the workshop was also in ICSE 2023, but we want to improve a bit the schedule and the outline of the workshop with these points. We want to coordinate more with the similar workshop. We notice that there are similar workshops in other flagships, software engineering venues, and coordinate more with these workshops will bring new research in the field. So we to continuously foster research in the field. We want to coordinate more with other workshops in SEB News. We want to involve more industrial subjects and practitioners, and promote discussion panels around current and relevant things. Finally, just a minute. Finally, we want to encourage the design, implementation, and the public availability of usable and high-quality tools to deal with NLBSE related challenges. About this last point, we have a special issue accepted at the Science of Computer Programming Journal. We invite all of you to submit your tools for the natural language-based software engineering. The call will open on June the 1st, and we invite all of you to submit your tools. Goodbye, and see you soon. See you next year.
Bye, everybody.
Goodbye, everybody.
Thank you all.
Thank you all, guys.
Thank you. Bye.
Bye-bye.
Bye-bye.
Thank you, everybody. Bye-bye.
Thank you. Thank you.
Bye.
Guys, I think that we can stop the registration and we can stop the call. Oscar, are you here? I will try to stop the registration. Young, are you here? No, we need. Okay. Yeah, can stop recording. I see Young here, but she's not responsive.